So a solution can be composed of two solids, two liquids, two gases, a solid and liquid, any combination. Aqueous solutions are very common. In aqueous solutions, water is the solvent. The solute can be a gas, liquid, or a solid. And so here are some common types of solutions. A solid-solid solution. How do you have that? Well, an alloy, such as brass or stainless steel, is going to be a uniform mixture of two or more different metals. And then things like gas dissolved in water would be things like club soda or any carbonated beverage. So any one solvent will not dissolve everything. And so we define solubility as the amount of substance that will dissolve in a particular amount of a given solvent. And that solubility is going to depend on nature's tendency towards mixing, but also on the types of intermolecular forces that the solvent and the solute have. And so we can think of the types of intermolecular forces as being a little bit like what language they speak. So physical systems tend towards lower potential energy. What's interesting here is that the formation of a solution doesn't necessarily lower the potential energy of the particles, and yet it still happens. So here, instead of liquids, we're looking at two gases inside of a container. If we remove this barrier, just like the fresh water and the seawater, these two gases are going to mix together and form a uniform solution. Does that lower the potential energy of the constituent particles? No, it doesn't. So then why does it do that? And the reason is entropy. So entropy is a measure of energy randomization or energy dispersal in a system. It's energy spreading out. I mean, if you take Chem 1B, we'll learn more about entropy in Chem 1B. But what happens when those two ideal gases mix is that the kinetic energy of each gas becomes spread out or dispersed over a larger volume. And so the entropy of the system has increased. Entropy is also often described as the amount of disorder, which is certainly easier to understand, but it's really about the dispersal of energy. So the reason that substances mix is due to this pervasive tendency for energy to spread out whenever it's not restrained from doing so. So substances mix due to entropy. Entropy also explains the transfer of thermal energy from hot objects to cold objects because energy wants to spread out. Any questions? So what about the effect of intermolecular forces? Well, these can promote formation of a solution or prevent it. So here we're looking at dispersion forces. So heptane and pentane both have dispersion forces as their only type of intermolecular force. These are two nonpolar molecules. They are likely to be soluble in each other. Remember, like dissolves like. Here we have dipole-dipole forces between acetone and chloroform. Here's hydrogen bonding between ethanol and water. And then here we have an example of the ion-dipole force between a sodium ion and water. So we have these forces between these particles. So we have intermolecular forces holding the solvent molecules together, holding the solute molecules together, and then also affecting the solvent-solute interactions. So like dissolves like. If the solute and solvent have similar intermolecular forces, a solution will probably form. So if we think about this as being like a language, and you think about people mingling together, right? So my ancestors came from Sweden, and my husband's ancestors came from Japan. So I'm going to use those two nations as my example. So let's say that these are, the solvent is just, a bunch of Swedes, and they only speak Swedish, which isn't true because almost all of them speak English too. And the red ones here are Japanese that only speak Japanese, and again, most of them also speak English, but we'll pretend that doesn't happen. So if you've got a bunch of people that only speak Swedish and a bunch of people that only speak Japanese, are they likely to mingle in a crowd and get to know each other? No, because they can't communicate, right? So these molecules will not form a solution if their intermolecular forces are very different from each other. Okay? The word miscible describes two liquids that are soluble in each other in all proportions. I think we did see that word before. Miscible is kind of like mixable. So if we've got solute-solvent interactions that are weak, then the gain in entropy from the mixing doesn't make up for the loss in energy, and a solution won't form. If the solute-solvent interactions are stronger than the original interactions, a solution will form. If they're approximately equal, a solution will form, because we still have entropy driving things, the spreading out. But if the interactions between the solvent and the solute are weak, like in my example of the Japanese and the Swedish people, their interactions with each other are stronger, and so the solution probably will not form. So this is a sort of question you could expect on an exam. Determine whether each compound is soluble in hexane. So first question, what is hexane? It's a hydrocarbon, right? So it's got carbons and hydrogens, okay? That in itself, just knowing it has carbons and hydrogens, means that it only has carbon-hydrogen and carbon-carbon bonds. So it must be nonpolar because all the bonds are nonpolar, right? So this is a nonpolar substance. We need to be able to recognize that. So hexane's nonpolar. To determine if each of these is going to be soluble, we're going to identify, well, is it polar or nonpolar? So what about water? Is water polar or nonpolar? It's polar. So will it dissolve in hexane? No. How about ammonia? It's polar. It's hard to tell from looking at NH3, but if we look at its Lewis structure, we got lone pairs on the central atom. So that's also polar. Again, will not mix. There's propane. Is that polar or nonpolar? That's nonpolar. It's only got carbons and hydrogens. So should that mix with hexane? Yeah, it should. And what about HCl? That one's also going to be polar. And that's where I said, here we have one bond. If the bond's polar, the molecule's polar. If those are two different elements, you should assume that it's a polar bond. So that one's polar and won't dissolve. Any questions? This is one of those questions that, seems like you're supposed to have memorized a bunch of stuff, and actually not. It really comes down to identifying the polarity of the molecules And we're not going to try to trick you with anything.